Today we will discuss a new chapter in this subject, which is chapter 4, and we will discuss about numerical differentiation. And this chapter is about differentiation. I know all of you already know about differentiation, but today we will discuss about the numerical technique in differentiation. And here is the introduction why we need a numerical differentiation, and basically we will talk about the derivative. Let's say we have a function f. Let's say it is a function of x, and how we can find the first derivative of a function of x by numerical, or maybe we can extend how can we find the second derivative and third derivative for this function by numerical method. And here is there are some explanation or what the reason that underlying behind the numerical differentiation. And so in general, what I want to stress is here, in general, numerical differentiation is the process of finding the numerical value of a derivative. So let's say we have a function, and usually in numerical, if we do experiment, we have the value at each point, so that we want to know what is the value. We can approximate the function from that value at each point, and then we want to know what is the first derivative, second derivative, third derivative, and so on by numerical. And here it also say that two situations where numerical differentiation is required. The first one is the function values are known, but the function is unknown. We also can find the differentiation of all this value, and also the function to be differentiated is complicated, and therefore it is difficult to find the derivative. And so in this second case, what we must do is we need to use the numerical technique to find the derivative of our function. And I can say that this chapter is not too long chapter. What you need to do, or what you need to understand is you need to know how to use all of this formula, because everything, all of this formula, for example, here is the first derivative, and you also will be given the second derivative, third derivative, and so on in your table of formula, so that you just need to apply and how to use it. So for example, here for the first derivative, we have 1, 2, 3, 4, and 5 different formulas that we can use to find the first derivative of any function, of a function, if we are given a function. So actually everything here all of this formula we can derive by the Taylor series. If we remember what we learned in previous semesters, the general formula for Taylor series is given as, let's say we want to approximate at the point fx plus h, where h now is a grid spacing. After this I will explain, and then we can expand this by using Taylor series plus h f prime x plus h square f double prime x divided by 2 factorial, or 2 is equal to 2, and then plus h cube f triple prime x divided by 3 factorial, or 6, plus dot 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 dot. And let's say now we want to get, or we want to know what is the, we want to approximate what is the value of f prime. So that what we can do is, you can bring this f x to the left, so that what you will get is h f prime x plus h square f double prime x divided by 2 plus h cube f triple prime x divided by 6 is equal to fx plus h minus fx. And what we want is, here, if we divide everything by h, we divide both sides by h, what we will get is f prime x is equal to fx plus h minus fx divided by h. And at the back here, usually what we have is, we write like this, plus order, or big O of h, because if here is the highest order of h is 1, because everything here, the second term here, if we divide by h, so that what we will get is order h is the highest one. And this last term, usually in numerical, if you try to read in numerical books, this one is called truncation error. So that what we want to find is the first derivative of our function here by using two value. So meaning here is a two value. We have two value, fx plus h minus fx divided by h, or this formula also can be illustrated by using this figure. If you can see here, let's say now we at the base point, or any name. So here I call it xi. Here we have xi, and the exact tangent, or the first derivative that we can find, is this line. And by numerical, what we can do is, we can have three formulas to find the first derivative. So for this formula, f prime x is equal to fx plus h minus fx divided by h is the blue one, because here, let's say now here is the different, here is h. So we have at this point is fx plus h, here is fx plus h, fx plus h, and here is our fx, and we minus this one. And so, or between this one, the difference between these 2 points is h, where usually we call it as grid spacing. And this formula, we call it 2-point forward difference, because we use, in this figure, we use the next point here, fx plus h. So that's why we call it 2-point, because we only take 1 point here, 1 point here, and another point here. We also can have 2 point backward, where we take this one also is h. So let's say difference between these 2 points is h, so that we can have f prime x is equal to fx minus fx minus h divided by h, which is the second formula here, fx minus h. And we also can use 2 points, first one here, and the second one is at the point A, so that The difference between these 2 points is 2h here, you can see. So that's why in that formula, we will have f prime x is equal to fx plus h minus fx minus h divided by 2h, which is the third formula here. And oh, I'm sorry, here it is a 2 point. No, it's a 3 point. Yes, it is a 3 point because it involved with 3 point. So here we also can have a 3 point backward difference, and this is the formula given, and we also can have 5 point central difference formula, which is this one. And that is a little bit explanation how we derive that formula for the first derivative. And actually you can go on for the second derivative. Here is the second derivative. If you see here how to find the second derivative, and also how to find the third derivative, and so on. But for you no need to worry because everything is given. So now let's say we want to understand how can we use this formula by using this example. Given the values of fx is equal to x exponent x in the table here, this is what I said just now. At every point we have the value of our function, and now we want to find the first derivative at point here. So by using 2 point difference formula, and we also need to find its absolute error. So what we need to do here is we need to find f prime 2.0. And of course what we need to know is we need to know what we have. All the value here is given in the table, and by looking at the table we know the difference between the point. We know that the difference between 2 point, this one, the difference is h is equal to 0.1. So let's say now we write is equal to f x plus h minus f x divided by h. So now let's say here we use the 2 point forward difference formula, and then after that we just substitute. Our x here is 2, so meaning that here we have 2.0 plus 0.1 minus f 2.0 divided by 0.1, and what you will get is f 2.1, which is this one, 17.1489 minus f2 is this one, 14.7781, and everything here is divided by 0.1. And you can calculate by using your calculator as usual, and the answer here is 23.708. And we also need to find the absolute error here. So what is the absolute error? Absolute error meaning that we need to find the exact value of this f prime x minus, let's say this one is the exact one, minus f prime x for approximate. Let's say I use the symbol of bar here, stand for a numerical value, so that we have the absolute error. So this one, the value for the numerical value is 23. This is the value here. But now we need to find what is the exact value. So first, to find the exact value, of course we need to find our first derivative of our function. So here what we need to do is we need to apply the product rule. So product rule, and the product rule is given by f prime x is equal to, let's say now it is a uv. uv prime plus v u prime. So now we have x exponent x plus exponent x, and our meaning here that our x now is 2.0, so the exact value is equal to 2 multiplied by exponent 2.0 and then plus exponent 2.0, so that the exact value of first derivative of our function is, if you calculate this one, this value, all of this value, what you will get is 22.1672. So that the absolute error, so absolute error is equal to 22.1672 minus 23.70, and what you will get, I think what you'll get is 1.540 ik. So this one is the answer that we use by using everything here. Everything here we use the 2-point forward difference. 2-point forward difference. So now let's say we want to use the 2-point backward difference. So now let's say we want to use now B 2-point backward difference formula. And the formula given here is f prime x is equal to fx minus fx minus h and divide by h. And so meaning that f prime 2.0 is equal to f at 2.0 minus f 1.9 divided by 0.1. And then you can use the table. F, your function at 2.0 is 14.7781 minus f, your function at x 1.9 is 12.7032 divided by 0.1, and the answer that you will get is 20.749. So again, we need to calculate the absolute error. So absolute error is equal to the exact value. The exact value, we can use this one, the same one here, 22.1672. 22.1672 and minus this one 20.749, and so that the absolute error that you will get is 1.4182, or it is the error. So if you see here, the error by using 2-point backward difference is small than the error by using 2-point forward difference. So meaning that for this example, or for this case, 2-point backward difference is a little bit good compared than 2-point forward difference. But now we also have, for the first derivative, we also have 3-point or 2-point. 3-point central difference. We have 3-point central difference formula, where we need to divide because we use a 3-point. So the formula given here is fx is equal to fx plus h minus fx minus h divided by 2h. And so meaning that implies that f 2.0 is equal to f 2.1 minus f 1.9 divided by 2 multiplied by 0.1, you will get 0.2. So that you just use the table, everything is given. Here is 17.1489 minus 12.7032 divided by 0.2. And here what you will get is 22.2285. And as usual, you also can calculate the absolute error. The absolute error is equal to absolute, the exact value, the value is 22.1672 minus 22.2285. So that what you will get here is 0.0613, and it is a pretty small. The error is quite very small, so that meaning that here it shows that you need to use first, of course, if you want to have a good approximation for the first derivative, or to find the derivative by numerical, I can say that you have two things that you need to consider. First, you need to consider so many points, and the other thing is small grid spacing, because if you still remember here, we want to find the derivative at C here, or the tangent at the point C here. If we have our grid spacing H here is very small, pretty small here, so that we can get as close enough to this tangent point C. So that is the implication about this first derivative. And here is the example. That we can ask you in the final exam. So the example is not too difficult. A car is traveling at a constant velocity at time 0. The driver applies the brake with distance x travel at specific time. So everything is given. So you have the data. You have data here at first, second, and second 2, 3, 4, and 5, and then what happened to your car, and then they ask you to estimate the velocity dxdt at t4, and then you need to use 3-point centered difference formula. And 3-point centered difference formula is this one. You have f prime x is equal to fx plus h, then minus fx minus h divided by 2h. So for here, your h of course is 1, and then you need to use this value and this value, and then divide by 2 multiplied by h, where in this case your h is 1, and then after that you just use your calculator to find what is the velocity v here, and the marks is very small, only 2 marks. Okay, so this one is about the first derivative.